So even more common than the virtual spring, as a building block of virtual environments, people really like to use virtual walls. The idea being that a virtual wall is now an environment that you aren't interacting with all the time necessarily in your virtual environment, but it's a haptic object that you can encounter. So in this sketch over here, we have a user who is hanging out outside the virtual wall, and the virtual wall is infinitely deep, represented here, and then this line right here is the entry into the virtual wall. And we're defining this over here as the positive x direction. And as we saw with the virtual spring, the sign was really important, and so we want to make sure that this has the right sign. So what happens as the user starts moving into this virtual wall is eventually you cross over the barrier, and then you wind up inside the virtual wall. And so you need to compute what is the penetration depth of the user into the virtual wall. And we're going to use a spring to try to push the user back out with a certain force. And for that, what you can imagine is that if you have this virtual wall here, and you have the user who's sitting here, the idea is that there's a spring attached to the surface of the virtual wall that is trying to pull the user back out. So that's actually what's going to be generating this force. And so similarly to rendering a spring, we need to use an F equals kx type equation, except now we need to account for the fact that there's a new equilibrium point. It's not just zero, it's wherever the position of the wall is. And the other thing we need to make sure of is that this is free space over here. So on this side of the wall, we have free space, and the user shouldn't be feeling any forces over there. So sometimes we call that a unilateral spring rather than a bilateral spring, because you only feel the spring on one side of the wall. So the equation that actually gets you there is this one. It says if x user is greater than x wall, and this part here is a really important step. This is the collision detection. That occurs when we try to find out, are we inside the virtual wall or not? And if the answer is yes, if x user is greater than x wall, and this is a greater than sign because positive x direction is defined this way for the virtual wall and the way we've drawn it, if x user is greater than x wall, then we compute the force as follows. F equals k times x wall minus x user. And the sign convention here is such that the force will be pushing in the negative direction to push the user out of this wall where the wall is on the right-hand side of your screen. And of course, just like in the example with the virtual spring, the stiffness is assumed k is greater than 0.